Good morning and welcome to the final ATCO SpaceLab Speaker Series session of 2023. We look forward to inviting you to our exciting lineup for 2024 soon. My name is Claire Porbay and I'm a member of ATCO's transformation team, and I am pleased to be your moderator today. I'd like to begin by acknowledging the Indigenous peoples that are traditional custodians of the land that I am on today. As this is a virtual event, I encourage us all to reflect on the meaning of place, and in doing so, recognize the various traditional, ancestral, and unceded lands on which ATCO conducts business. I do this to reaffirm my commitment and responsibility in improving relationships between nations and to improving my own understanding of local Indigenous peoples and their cultures. I'm honored to live and work in Treaty 7, the traditional territories of the Blackfoot Confederacy, Niitsitapi, comprised of the Siksika, Kainai, and Piikani Nation, the Tsuut'ina Nation, and the Stoney Nakoda, including the Chiniki, Bearspaw, and Goodstoney First Nations. The city of Calgary, Mohkinstsis, is also home to the Métis Nation of Alberta, Region 3. And I'd also like to pay my respect to elders, past, present, and upcoming in the communities and regions where we operate. Our speaker today joins us from the University of British Columbia, Okanagan. The UBC Okanagan academic campus is situated on the traditional, ancestral, unceded territory of the Syilx Okanagan Nation. Now, a quick comment on the lecture format before we get started. Today's lecture is a one-way video and audio format. Please ask questions by using the question icon to the right of your screen, and we'll open the ability to type in your questions shortly after starting today's lecture. I encourage those of you who are new to today's topic to approach this time we have together with a growth mindset. We're certain that if you do, you'll walk away today having learned something new, like how to say thermally stratified atmospheric boundary layer, which took me a few times to practice saying before today. I'd now like to hand it over to my friend and colleague, Dr. Nisha Mohan, Principal Transformation Lead of Science and Technology with ATCO's Transformation Team, to introduce our speaker today. Over to you, Nisha.
Thank you, Claire. Thank you all for joining today. We are thrilled to have the distinguished Dr. Joshua Brinkerhoff join us today, an accomplished associate professor and the associate director of research and industry partnerships at the School of Engineering, UBC Okanagan. Leading the UBC Okanagan Computational Fluid Dynamics Laboratory, Dr. Brinkerhoff's team is finding solutions for the crucial industrial, agricultural, and environmental challenges of British Columbia's interior, as well as globally. His lab focuses on understanding the limitations of scientific tools in wind energy site assessment, aiming to enhance the efficiency of wind energy plant designs by delving into the physics of turbulent fluid flow. At ATCO, we remain committed to our sustainability goals and specialize in harnessing the immense power of renewable resources. Our renewables portfolio today includes a 232 megawatt of wind power, and we are actively working on developing an additional 620 megawatts. We view today's lecture as a learning opportunity aligned with our pursuit of expanding our wind power initiatives. Today, Dr. Brinkerhoff will share the advances his research team made in modeling the aerodynamic losses experienced by wind farms to a better accuracy by considering the interaction of the wind farms with the thermally stratified atmospheric boundary layer. Wow, that phrase is a mouthful, but I'm looking forward to learning more about it from Professor Brinkerhoff. We are honored to welcome an expert of his caliber and eagerly anticipate the enlightening session ahead. Dr. Brinkerhoff, the floor is yours.
Thank you very much, Nisha. Some of those words really are a mouthful. Thank you for having me here, and thank you for the opportunity to give this presentation of the activities of my research team. Let me begin by acknowledging that I'm joining you from the unceded historical and ancestral territory of the Syilx Okanagan people. The talk that I'm going to give today is entitled Advances in Modeling Wind Farm Blockage in Thermally Stratified Atmospheric Boundary Layers. And it may sound complicated, but what we're saying there is that the boundary layer, which is a surface layer of air over the surface of the Earth, merely just has a variation in temperature, and that variation in temperature creates challenging obstacles when we're trying to operate a wind farm in consideration of the physics of the atmosphere. But let's begin a little bit further back. I want to talk about the losses that wind farms experiences, and I'm going to talk about the interaction between the wind farms and the atmosphere in which they operate. I'm going to talk about the way that the wind farms interact with the atmospheric boundary layer and how that affects the losses and the kinds of losses that are going to be that occur. I'll talk about the simulation tools that my team is developing and using to understand these problems. And then I'll also talk about advances in developing low-cost models, engineering models, to better predict these and operate wind farms in a more profitable and optimum manner. The motivation for the look at renewables, of course, is triggered by our growing appreciation for the major changes our world is facing in a changing climate. The picture I'm showing here is taken from August of earlier this year from Kelowna, where I'm joining you from. And it's looking towards the west side of the Okanagan Valley. And you can see that the entirety of that mountainside is on fire. And this is just one of 2,200 fires that burned through British Columbia in 2023, consuming more than 2.5 million hectares of forest and costing probably in excess of $800 million, even just now, not counting future impacts, and also driving an evacuation of tens of thousands of people within the province. My own campus was evacuated for a week, and this is becoming a new normal. And I show a picture in the image where my childhood home was located. Thankfully, it wasn't burned, and my family doesn't live there anymore. But we are not thinking of climate impacts as a mere theoretical anymore. And this is motivating us to make the real changes system-wide to address to these changes. So in response to these climate impacts, Canada has established emissions target reductions. And the targets that has been set are based on the 2005 levels. And so by 2030, Canada, the Canadian goal is to be 40 to 45% below 2005 levels. And that means 2005 emissions were about 739 megatons of carbon dioxide equivalent per year. And the reduction is not happening as quickly as we would like. And so, for example, 2019, only 730, so a small reduction in carbon emissions. And to reach our goal of 2030 emissions and then zero emissions by 2050 is going to take some challenge. And the Canadian Renewable Energy Association has made a prospective position on how can Canada achieve its greenhouse gas emissions targets. And the comment that they make is that we need to increase the amount of renewable energy that's currently installed. And so what I've plotted here is two curves. The large one is the total megawatt installation of wind and solar capacity, and the inset is the installed wind capacity in Canada, and these are in megawatts. And the green is the historical trend up till 2020. And the red circles correspond to a reference scenario where the growth is kind of business as usual. An evolving policy scenario is the gray, but the Canadian Renewable Energy Association 2050 vision is in the blue. And what they envision is a significant increase in the total installed wind in order to achieve the Canadian greenhouse gas emissions reduction targets. So just as a context, to achieve the vision to get to net zero by 2050, the total installed wind capacity needs to almost increase by a factor of 10, from 15 gigawatts about installed capacity in 2022 to over 100 gigawatts capacity in 2050. And that's a significant increase. And that means that we're going to have more wind farms to achieve that goal, and the wind farms themselves are going to get bigger. And this is a trend. We see wind farms already are growing, and wind farms are getting more crowded. And I have just a few illustrative examples of this. So this is near the Gulf of St. Lawrence, where we can see within about 5 to 10 kilometers of each other, significant number of wind farms in the around 50 to 100 to 200 megawatt range. And how do these wind farms interact with one another? how do these wind farms within close proximity affect each other's performance? And when you have such a density of capacity, how does that interact with the surrounding atmosphere? These are important questions. Here's another example. This is even more dense in the south of Ontario, where we see wind farms essentially going up right next to the neighbor, continuing on right next to the next neighbor, where we have a very high density of wind farm installation. And again, further questions. How do these wind farms interact with one another? How do they interact with the atmosphere that they're surrounded by? And a last example in Alberta. I thought that an Alberta example would be necessary. So this is in the south of Alberta, and we see farms getting larger, 100 plus, 200, 300 megawatt farms, and also much more crowded in close proximity to one another. And so this provides a bit of context around why we want to understand the interaction of wind farms with each other and the interaction of wind farms with the atmosphere in which they operate. To understand this problem more better, let's look at the ways in which wind farms interact with the atmosphere. And to do that, let's remember that the atmospheric boundary layer consists of relatively steady winds at high elevation, above 5 to 1,000 meters from the Earth, and then a profile of wind that goes from that high geostrophic speed to a much lower speed and then ultimately zero near the ground. And that wind is what we refer to as the atmospheric boundary layer. And the profile of that determines the stability of the boundary layer, the amount of mixing that the boundary layer experiences, etc. And the boundary layer itself is not a steady flow, rather it's turbulent. And so we have a cascade of turbulent eddies at various scales and space and time that are enhancing the mixing that's taking place within that layer. And so when the atmospheric boundary layer interacts with a wind turbine, the wind turbine removes momentum from the flow to generate energy, to generate power. And as a result, there's now a deficit in momentum or a deficit in kinetic energy in that wind. And so that creates a small wake behind the wind turbine. And there's not just one wind turbine in a wind farm. There's clusters of turbines, and each of those will have their own wake. And the wakes will interact with one another and coalesce. And the wake of not just a single wind turbine, but the wakes of the farm as a whole will then flow downstream of the farm and may interact with the wakes of an adjacent farm. And when we talk about a wake, it's similar to a wake behind a boat. And what we see is that there's a deficit of kinetic energy in that region of flow. And so a turbine subjected to a previous turbine's wake is going to generate less energy. There's less kinetic energy in the wind for it to extract. And that's referred to as wake losses. And when the wake behind a turbine mixes with the turbulence in the atmosphere, you can get a re-entrainment of mean kinetic energy that allows the wake to re-energize. And so the spacing of turbines becomes very important, and the spacing of farms becomes very important. So here's a picture where we can illustrate the wake in a turbine. This is offshore, and the wake has less kinetic energy, and that also means that there's a depression in the static pressure. And what we see is the fog in that image highlighting the presence of the wake and the interaction of one turbine wake with an adjacent turbine. But the question, of course, is not just how one turbine wake interacts, but how do all the turbines and the wakes behind the turbines in an individual farm interact with one another? And what we see is that the wakes are not necessarily superpositionable. We can't superpose them and account for the losses. They interact in highly nonlinear ways. And then, of course, the other important question is farm interacting with adjacent farms and how close farms are spaced and the way that wakes interact from one farm to another. And then a final comment. Wind farms themselves are getting much, much larger. And the amount of energy being removed from the atmosphere means that the wind is feeling a significant deceleration. It would be like trying to walk through water that goes up to your waist. It just slows you down. And the atmosphere experiences that slowdown as a blockage. And so this phenomena of the slowdown of the wind approaching the wind farm is referred to as wind farm blockage, sometimes called induction. And it can lead to severe power losses, especially when the atmosphere is strongly stable. And presently, the wind farm blockage is not well modeled by engineering models. And their blockage actually is a superposition of two simultaneous phenomena. Local blockage arises from the pressure created upstream of a turbine because the wind feels the presence of that turbine and it slows down in response. That's local blockage. It's observed from a local pressure perturbation of an individual turbine. But then the sum of those individual blockages is less than the total global blockage that we see arising from the interaction of the farm with the atmosphere. So global blockage is the sum of the individual blockages plus an additional interaction with the atmospheric boundary layer. I mentioned that wind farm blockage, especially the global blockage that results from the interaction between wind farms and its atmospheric boundary layer, has not been well understood. In 2019, one of the world's largest wind farm operators, Ørsted, released a report where its rate of return had to be reduced because it was determining that it had over-predicted the amount of energy its wind assets in the North Sea could produce, and they were producing much less than what was expected. And this was created a significant ripple effect throughout the industry for other operators as well, where blockage effects as well as wake losses were not well predicted. And it highlighted an industry-wide problem where the interaction between very large wind farms and the atmospheric boundary layer and the wind farms adjacent to the wind farm in question was being inadequately predicted. Okay, now I mentioned that the interaction of the wind farms with the atmospheric boundary layer was not well understood. And the reason for that is because the wind farms themselves are so large that they can actually trigger gravity waves in the atmospheric boundary layer. And a gravity wave is just a displacement of the boundary layer of the flow. So you can see a small oscillation in the atmosphere. And there are two types: interfacial waves, which are two-dimensional waves that travel kind of parallel to the Earth, and internal waves, which are waves that travel perpendicular to the Earth, kind of out into space, if you like. And the interfacial waves develop in this inversion layer where we have a change in temperature across a certain distance and height and above the atmospheric boundary layer. And this is where thermal stratification exists, where we have an adjustment in the temperature of the air. And what happens is when the wind hits the wind farm, it gets displaced upwards. And so now you have cooler air that's moving up and it's denser. And so it cools down, it wants to come back down. Where it gets warmed up, it becomes lighter and it goes back up. And so you end up getting this oscillation in the atmospheric boundary layer, which we refer to as gravity waves. And the gravity waves are determined by the inversion strength, which is the change in temperature that occurs across the atmospheric boundary layer. And it's also a function of how strong of interaction they have with the wind farm. And so what I've shown here is two, on the left bottom picture, two profiles of temperature versus height. H is the vertical direction. And A and B correspond to two different stability conditions of the atmospheric boundary layer. And then on the right-hand side, we see a picture of the pressure in the wind farm, around a wind farm, and the layer that's dashed with a dashed line corresponds to the boundary layer height. And we can see that the wind farm triggers a perturbation. The boundary layer moves up and down. And because the boundary layer moves up and then down, you get a local speed up or slow down of the wind triggered by the gravity wave that the boundary layer creates. And this is why blockage has been poorly understood, because the interaction with the atmospheric boundary layer and the gravity waves in the atmosphere with the wind farm has not been appreciated and taken into account in existing engineering models. Let's move on to the next slide. This is a picture of radar measurements from a satellite Sentinel-1 satellite from the European Space Agency, and this is looking at wind farms offshore in the North Sea, north of Germany and the Netherlands. And this just highlights the importance of clusters of wakes between different wind farms. And it's a little bit difficult to see, but what we see, those darker gray regions, measure the perturbation of the sea surface as a result of the wake from a wind farm cluster. And we can see the wind farm cluster from one wind farm living for a very, very long time, merging with the wakes of a neighboring wind farm. And they persist much, much longer than what was predicted by the individual wake models for an individual turbine. And that means that farms that are adjacent to one another will interact. And when you have a wind farm installed in a certain location, if another wind farm is installed in proximity to it, your power may go down. And that's obviously lends itself to some challenges and even legal challenges in the way that the wind farms interact. So understanding the interaction is really essential for optimizing the performance of these wind farms. So to understand these challenges, we need to use very large-scale numerical simulations. And I'll talk about why that is. And I'll talk about the advances that we are making in the types of tools that we can use to understand these processes. So to resolve the ways that wind farms couple with the atmosphere, we need to account for all of the relevant physical processes. That includes the atmospheric turbulence, which may itself be affected by how stable the atmosphere is. And to understand the turbulence and to capture the interaction of the turbulence with the wind farm, we need to be able to simulate that turbulence as well as simulating the wind farm. And doing both together is challenging. And the way that is typically approached is to run separate simulations, one for the turbulence entering the wind farm and another one for the wind farm, and then merge them together. And that's what we've developed. It's called a concurrent precursor method, where you concurrently run both simulations. You take the turbulence that you generate in one simulation and you feed it in as input to the wind farm simulation. And not all existing codes allow for this concurrent precursor to capture the turbulence in the atmosphere and the stability of the atmosphere interacting with the wind farm. And so what we have in the table here is a list of different software codes that are either open source or closed source, available to industry or being used in academia. And the bottom category is the code that my team uses. It's called TOSCA, and that stands for Toolbox for Stratified Convective Atmospheres. We've open sourced this code so other researchers can use it to understand the kinds of questions that we're trying to understand. And we capture all of the various physical processes that are necessary to do, including special treatment of boundaries to prevent wave reflections and other things. And we've tested it on the largest supercomputers in Canada, and we've demonstrated that our code is very scalable. So you can run the code very efficiently on very, very large numbers of computational nodes, a large number of compute processors, if you like, and also can be used for capturing the effect of terrain if we're looking at onshore wind farms. So again, TOSCA is the name of our code, Toolbox for Stratified Convective Atmospheres. We solve large eddy simulation. And what large eddy simulation means, LES, is that we capture all of the turbulence almost in the flow. There's some smaller scales of turbulence that we're not capturing, and that means the smallest eddies that are spinning the fastest are not captured. We have to model those. We account for them. But all of the rest of the turbulent eddies that are present in the atmosphere, we capture. And the turbulence that is created by the wind turbines in the wind farm, we capture that as well. We capture the buoyancy forces, we capture the Coriolis forces that are created within the atmospheric boundary layer as well. And we capture the effect of wind turbines by adding a body force term to our governing equations. The wind turbines themselves are expensive to solve because they're complex bodies that are rotating in the flow, and to capture their interaction with the atmospheric boundary layer is expensive. And so we've implemented in our code a number of lower cost models that represent the effect of the wind turbines, maybe without necessarily having to resolve each individual feature of those wind turbines. And these different actuator models are varying levels of fidelity, and we can compare them to field measurements and to other benchmark simulations to ensure that the simulations are accurate. The picture on the right-hand side shows what we call scalability of the code. If we run the code on more and more CPU nodes, bigger and bigger computers, does the code still run efficiently? And what we've demonstrated that up to 80,000 cores, so 80,000 processors, the code scales very well. Let's go on to the next slide. So just to show some pretty pictures associated with running this code, it allows for us to conduct very detailed numerical simulations of one turbine or hundreds of turbines. We resolve or we capture the effect of individual turbines using various actuator models, actuator disk models, line models, and advanced actuator line models that are more highly tailored to capture the detailed, intricate features of the wind turbine. We can capture complex terrain using a immersed boundary method, and we can have the turbine itself immersed in the flow and rotating around, as pictured by the vertical axis wind turbine that's captured. The code is open source, and I provide a link in the slides, and it can be freely available for other research teams to use. So we don't want to just run a code without knowing it's going to work. And so here we've presented validation of the code. And what we've done is simulated a isolated wind turbine, and then we model the wind recovery downstream of that wind turbine, as well as clusters of turbines. And the three pictures that are shown here compare our Tosca code in black to the existing kind of benchmark software codes that are being used within the wind industry. And what we see is that we're able to capture the mean wind speed, we're able to capture the wind veer, the change in direction in the wind turbine downstream of the wind farms. We're able to capture the turbulence, we're able to capture the recovery of the velocity downstream of the wind farm very well. And the agreement is very good. So to save on computational resources, we run our code to capture the effect of the turbulence as well as the wind farms themselves in a specialized way. And we've developed a hybrid, what we call hybrid offline concurrent precursor method, and it consists of three phases. Firstly, we run a small little simulation of the turbulent atmosphere in a region, very small region, that's much too small to capture the entirety of the wind farm. But once we have that running, we periodize it. We take a copy of that and we stretch it in the spanwise direction, so around the front of the wind farm, if you like. We create a database of turbulent inflow. We map that into our large boundary condition, into our large domain with a wind farm. That's step number 2. And then in step number 3, we run these cases simultaneously. So we have simultaneous simulations running, one without the wind farm, one with the wind farm. The one without is feeding in turbulent inflow into the one with, and we have a mapping method that allows for that turbulence to be mapped in a natural way into our large-scale domain. And this allows for us to capture the atmosphere and the flow in the atmosphere accurately, and at the same time, the wind farm and the interaction of the wind farm with the atmosphere and the turbulence in the atmosphere accurately. And this is an important thing to understand the wind farm atmospheric interactions. The other thing that we really need to understand is the waves created by the wind farm within the atmospheric boundary layer. We want to capture these waves, and we don't want those waves to somehow pollute the solution. And we don't want any numerical artifacts to pollute the solution. And so we need to control the speed of the flow at the wind turbine height, at the hub height. We need to control the temperature so that we don't have our atmospheric boundary layer growing unnaturally. And we need to control the waves that we create in our simulation so that as they create and propagate the domain, they don't reflect off of the boundaries of our domain in an unnatural way. And so we've introduced a number of what we call damping layers. And the damping layers ensure that the wind farm created waves are not reflecting in an unnatural way. It ensures that the speed of the wind coming at the wind farm at the hub height of the turbine is controlled in a natural way, and that the height of the atmospheric boundary layer is controlled in a natural way. And this is very sensitive, and a big reason why the wave wind farm interactions haven't been well understood is because of the delicateness and the intricacy of the ways in which you prevent wave reflections within these simulations. So I'll just say that by implementing various specialized damping layers and controllers, we're able to ensure that our simulation is accurate. It's not polluted by numerical effects and can capture these nuanced interactions between the atmosphere and the wind farm. This is information about the 2 wind farm conditions that we've simulated. So these are non-dimensional parameters that select the wave interaction region, or the way that the wind farm interacts with the atmospheric boundary layer. And the 2 simulations we have correspond to subcritical and supercritical waves. Subcritical waves are ones in which, when the wind farm is immersed in the atmosphere, it triggers gravity waves that, subcritical case, move upstream and downstream of the wind farm. And in the supercritical case, they only move downstream of the wind farm. And so we would expect, under those 2 different atmospheric conditions, the effect of the wind farm and the interaction of the wind farm with the atmosphere is going to be quite different. Everything else is the same. The only differences between the 2 cases is this, that you have the different thermal stratification, and that causes different behavior in the interaction and the gravity waves that are triggered by the wind farm. And so here we have, in the top row, simulation results for a subcritical case. And this is for a wind farm that consists of 100 turbines, each 5 megawatt capacity, and arranged in 5 rows and 5 columns, 20 rows. And the top row corresponds to these subcritical conditions, and the bottom row of images corresponds to supercritical conditions. And in the left-hand side, the instantaneous velocity, it's very difficult to see any difference between the subcritical and supercritical atmospheres. But if we look at the pressure fluctuation in the middle set of images, we can see that, first of all, the pressure fluctuation creates these waves that emanate back behind, or emanating downwind of the wind farm. And they look like the waves that you would see as a swimming duck is moving through. And indeed, that's a very similar phenomenon. We have interfacial waves in the atmospheric boundary layer that are emanating downstream. And they also create this red region, which is a high pressure region upstream, and that's triggering the blockage and the reduction in power that the wind farm will experience. And then the final comment is, in the supercritical case, we see that they don't propagate upstream nearly as much, and the blockage is different. Whereas the emanation of the waves downwind occurs much more steeply. If you look at the angle of those waves, it's much more steep in the supercritical case. And so we want to understand and more importantly, be able to predict these variations in the blockage created by the wind farm under these different atmospheric conditions. So let's go to the next slide. Now, all that I've described to date highlights that capturing the wind farm interacting with the atmosphere is very complex, and it's very challenging to do, and it's very expensive computationally. And what we would like to do is to study that interaction, but to do it in a much cheaper way. These gravity waves, we recognize, have a major impact on the performance of the wind farm, but simulating them is very difficult and computationally expensive. Is it possible that we can capture those waves in a cheaper manner? And what we've done is developed a low-cost model, I'll talk about shortly, that can be used to predict the nature of the waves, the amplitude and their period and so forth, created by the wind farm. Once we've made those predictions, we can apply that to our wind farm simulation. And we can adjust the ceiling of our wind farm simulation domain to create those waves rather than us having to simulate them naturally. And that reduces the cost more than 50-fold in terms of the cost of the computational simulation. And so this is another novelty that my research team has been able to develop, where we learned about the waves by simulating them with full accuracy. Then, having learned about them, made a simple predictive mathematical tool that allows for us to simulate them in a much lower cost. This presents the wind velocity through the middle of the wind farm on the right-hand picture. And the black line corresponds to our high cost, high fidelity large eddy simulation. And the blue and the orange lines correspond to our much, much cheaper version of our large eddy simulation, where we don't allow the gravity waves to develop naturally. We impose a certain gravity wave condition, just the right condition that exactly mimics the natural gravity waves. And we see almost perfect agreement between the naturally produced gravity waves and the ones that we impose. And that shows that our gravity wave model, the way that we can impose the gravity waves, can be easily captured using this more simplified approach. So I'll provide a little bit of talk about how do we capture those. So essentially the displacement of our domain mimics the displacement of the boundary layer that would be obtained when we resolve our atmospheric gravity waves. And so we use a low-cost, what we call multi-scale coupled model, I'll talk about in a moment, to model the boundary layer displacement. Then we deform our mesh accordingly within the simulation, and allows for us to capture these thermal effects and atmospheric effects in a much more cheap manner. So the top picture here shows the original approach, where we resolve perfectly the gravity waves within the wind farm. The bottom layer with the green and orange and purple corresponds to where the wind farm lives. The top layer corresponds to the atmosphere that we have to resolve in order to allow the gravity waves to develop naturally. And you'll notice that the new approach is a small sliver in comparison to the original approach, where we have to simulate many kilometers up into the atmosphere in order to allow the gravity waves to be created. And so by doing this new low-cost approach, we get no gravity wave reflections. We have much lower cost to our simulations. We don't need to have these tuning layers, and it allows for us to model a broader range of conditions because the cost is so much lower. This provides another look at the impact. We can see the black line is the natural case, the resolved case, and the blue line corresponds to the modeled case. And we see the effect of resolving versus modeling the waves on the pressure fluctuations created by the farm are well captured in our model. The orange line corresponds to the low-cost model that we used to estimate the oscillation in the atmosphere, and I'll talk about that in a minute. A final case we did was one in which we have a rigid lid. So we assume that the atmosphere itself is perfectly rigid, and the atmospheric boundary layer can't rise or lower. And that's a kind of limiting case that demonstrates what would you see if you had extremely high atmospheric stability. What's the impact on the wind farm power? So again, this is plotting the row averaged power of your wind turbines. These are rated at 5 megawatts. They're operating at their rated wind speed, 9 meters per second. The first row you see has 2.5 megawatts of power, but then there's an abrupt drop. And that's as a result of the wake effects that we saw. But then on top of that, we see this kind of oscillation in the power among the different rows. And that's because of the gravity wave impact that results in this pressure oscillation, very large scale, over the wind farm power. And so we see these oscillations along the different rows corresponding to the presence of the gravity waves and the interaction of the wind farm with these gravity waves. And the other comment we can see is that under subcritical conditions, the blockage effect is much more pronounced and the oscillation in the wind farm power is more pronounced. Under supercritical conditions, the gravity waves are much weaker. They don't propagate upstream nearly as much, and the overall pressure fluctuation is much more smaller. And then a final comment is whether we do the very high expense resolved method or the lower cost modeled method to capture these gravity waves, the power and the thrust of the wind turbines is well captured. Similarly, the velocity that we see upstream of the wind farm and then within the wind farm and then downstream of the wind farm is well captured. And we're comparing here the black and the blue lines, and we can see overall the black and the blue lines give very good agreement. And what's most important to observe is the slowdown you see coming into the wind farm. So that means approaching along the horizontal axis 0 kilometers. And you'll notice that the slowdown occurs quite significantly very close to that 0 kilometer point. That's when your first row of turbines are. But we also have this gradual deceleration that occurs even 2 or 3 kilometers upstream. And that blockage, that is what we refer to as the blockage, is a significant impact. You're measuring a lot less energy that would be present than before the wind farm was put there. And that's the blockage effect that we're trying to capture. And you notice that it's well captured by our LES as well as our MSC model, which we'll talk about in a moment. And again, this is highlighting the boundary layer displacement is sufficient. If we impose the boundary layer displacement, it's sufficient to determine the ongoing physics inside of the boundary layer that results from the thermal stratification. So whether it's a subcritical case or a supercritical case, we can capture the oscillation in the pressure field merely by adjusting the height of our computational domain in an appropriate way. So now we have these tools. We have the high expense tool, we have the lower cost tool. What are we going to do with them? So we wanted to simulate a number of realistic real world turbines. And we've simulated the N4 cluster, which is a cluster of 208 turbines that are installed in the North Sea. So these are very large scale turbines operating offshore. And we wanted to capture the effect of the wind farms interacting with each other and the interaction with the atmospheric boundary layer. And we had to set the atmospheric boundary layer state. And so we took 2 years of historical data that came from satellite measurements, and we looked at the change in the temperature across the atmospheric boundary layer, the height of the atmospheric boundary layer, and the rate at which the temperature changes within the atmospheric boundary layer with height. And we took 2 conditions that correspond to kind of historical norms for the atmospheric boundary layer living at the North Sea. And that corresponds to the 2 pink dots we see in each of these cases. And in one case, we have highly stable conditions, and in another case, less stable conditions, allowing for us to capture the 2 different subcritical and supercritical conditions for our atmospheric gravity waves. So this is a picture of the pressure oscillations created by the wind farm. So this is the wind farm when you have north being in the y direction, the vertical direction. This is the view that wind farms have. The flow is coming straight across in the west direction, so pointing in the positive x direction. We have large-scale pressure oscillations that can be seen in the wake of the farm that are the result of our gravity waves. So those light gray, dark gray undulations in the wake are the evidence of gravity waves that are visible. We capture those using our lower cost modeling technique, but still captured. And you can see the effect of the turbulence also well resolved downstream of the wind farms. And we can see the interaction of the 2 parts of this wind farm cluster, the upstream kind of arrowhead pointing part interacting with the more rectangular portion of the cluster downstream, and the gravity waves interacting with each other. So using these tools now, we can assess the performance of this particular wind farm under these different atmospheric conditions. So let's go on to the next slide. This is an image that shows the instantaneous velocity. And we see a kind of consistent dark line that's horizontal, and you see 4 of them. And that's an artifact of the way in which we introduce the turbulence into the domain. It doesn't have an effect on the flow statistics. It's related to the way in which we periodize the inflow boundary conditions, and it doesn't have an impact. It's just an artifact in the simulation itself. But what we do see is a really quite beautiful presentation of the turbulence created by the wind farms as they evolve very far downstream. And we can see the propagation and the stability of a very long-lived wake downstream of the wind clusters and the interaction between the 2 wind farms themselves. And so this is providing phenomenal insight into how the wind farms evolve and how do they behave and how can we predict their behavior in a low-cost manner to better operate wind farms in a more optimum way. And that brings me to the final or the next topic, where we have these great tools where we can simulate the wind farm, but operators can't simulate wind farms whenever there's a question. We need low-cost engineering models based off of the physical insights that we glean from our very expensive simulations. So let me talk about that now. So the wind farm blockage that we've talked about up to now is essentially a problem that lives on multiple scales. We have scales associated with individual turbines, and we have scales associated with the large wind atmospheric boundary layer. And these 2 scales are coupled, and they communicate with one another. At the micro scale, that's the size of the individual turbines, an individual turbine creates wakes, and it creates its own local induction field. So the flow slows down downstream because of the energy taken away, and it also slows down upstream of that individual turbine because of the blockage created by that turbine. And the wind farm is an assortment of multiples of these individual effects. But it's not just superimposing those individual effects linearly. There's a nonlinear interaction between the small scale individual turbine scale and the large atmospheric boundary layer scale. And so we begin by creating what we call a multi-scale coupled model, where we couple the physics at the small scale with what's going on at the large scale. And we take what's going on at the large scale to then inform what's going to happen at the small scale. And these are coupled in an interactive way. And this requires a number of individual parts. First of all, we need a method to superimpose the individual small-scale wakes. Then we need to know, based off of the perturbations created by those, what is the effect on the atmospheric boundary layer. And then knowing the effect of the atmospheric boundary layer, we need to reconstruct a new wind speed that the local conditions are going to experience, and then allow this to occur in a highly, with feedback to one another. And so this is the big picture of what we call multi-scale coupled model. And in each of these different locations, we use low-cost engineering tools coupled in an appropriate way to capture their interactions. And that's the highlight I'd like to make mention of. My team has not invented too many of these individual parts, but what we've recognized based off of our large-scale simulations is the importance of their mutual interaction and the way that they couple together. And we've cobbled a bunch of individual models together in a manner that allows for us to capture their mutual interactions better than others have done in the past. So let's go on to the next slide, please. So to capture the wind created, or the perturbation of the atmospheric boundary layer by the wind farm, we break our atmosphere into 3 layers. One layer where the wind turbines live, a second layer above that, which we call the upper layer. It's immediately above our atmospheric boundary layer, and then a third layer called our free atmosphere. And then we average our governing equations vertically, and we have only 3 layers, so 3 equations in each layer, or equations for each layer. And these are the depth averaged, and we linearize the Navier-Stokes equation, so the equations governing the fluid flow in those layers. And by solving those, we can compute the pressure perturbation within our wind farm very cheaply, because we have only 3 equations and only in 3 layers. And also we can write these equations not in physical space, but in Fourier space. So we can solve them very efficiently in that way. Once we've done that, we have a modified set of 3-layer equations without the wind farm forcing, where we have pressure as a forcing term, and this fixes for us the eta term, which is the displacement of our atmospheric boundary layer as a result of the forcing from our wind farm. And so this gives us a set of new equations where we have the perturbation, if you like, created by the gravity waves. So to highlight the results, we're looking at subcritical conditions and supercritical conditions. The black line represents our very expensive large eddy simulations, and then the blue, orange, green, and red lines represent different engineering models. And to give a picture, a large eddy simulation will run on 40,000 CPUs for 40 hours. So we're talking about very expensive computational simulations. Whereas the models, the blue and orange and green and red, they'll run on MATLAB on one processor for 30 seconds. So it's much, much faster. So many orders of magnitude difference. The comparison allows for us to compare the quality in predictive ability of these different models. So the blue one is a wake model. That's where we only look at the individual effects of individual turbines. And an important thing is we cannot see the slowdown coming up to the wind farm using only the blue model, the wake model. Moreover, the effect of the individual turbines is underpredicted. The slowdown or the wakes, the strength of the wakes is not well predicted. If we add to a wake model what's called a vortex cylinder model, wake plus VC, so the orange one, we get a little bit of a picture of the slowdown in advance of the wind farm. So that's at 0 kilometers in the horizontal. But it still underpredicts the performance of the wind turbines within the farm. And it also doesn't do a good job of predicting the recovery after the farm. And the dashed vertical lines correspond to each of the locations of where we have wind farms, where we have wind turbines. The green model represents the 3-layer model that accounts for the gravity waves, but it doesn't have a proper coupling between the gravity wave effects and the local effects. The red model is ours. It's where we've coupled a gravity wave model based off of the 3-layer model, as well as a wake model and a local blockage model. And so it's that red line that does the best in terms of capturing the blockage effects upstream of the farm, as well as the capturing the velocity within the farm, as well as capturing the recovery to the undisturbed conditions downstream of the farm. And these the predictive ability of our model is consistent in the subcritical case as well as the supercritical case. This shows the ability of the model to capture the power and the thrust of the row averaged turbines in the farm. And what we see is that the wake by itself, the wake and a local induction model, as well as an uncoupled gravity wave model, are not able to properly capture the power or the thrust. And it was these models that are still industry standard practice for making predictions, either in advance of doing a site assessment or in operating the wind farm itself. And so it's because of the deficiency of these existing models, the blue and the orange and the green, that Ørsted operator in the 2019 made this announcement where they were over predicting the performance of their wind farm assets. And it's our red model, the one that's shown here, the multi-scaled couple model, that in our opinion, for the first time, captures these interactions in a physically meaningful way that allows us to make predictions, inaccurate predictions, very accurate predictions of the wind farm performance, accounting for the local effects at individual turbines, as well as the large-scale atmospheric boundary layer effects and their interactions. So this is a comparison between our LES, which is kind of the ground truth, and the different models. And the on the left-hand side image, the ones that are clustered around the diagonal are the most accurate. And so we can see the red image, the red pictures, which is our multi-scale coupled model, are much more accurately predicted. And if we look at the total prediction in comparison to our ground truth of the simulation, the existing engineering models all tend to overpredict the power, and by more than 9%, even up to 19% overprediction. Whereas our multi-scaled coupled model is much more conservative. It makes underpredictions consistently and to a much lower magnitude, even less than 3%. But now we're getting to an understanding of the limits of our multi-scale coupled model. The multi-scale coupled model has as its limit some constraints on the stability of our atmospheric boundary layer. And we want to relax those constraints. We want to be able to capture better the free atmosphere stability effects on our wake model for a heterogeneous wind in the background. And the wake model alone can capture the cluster wakes that live far downstream of clusters of wind farms. So what we're showing here is in the left-hand side, our LES simulation, which shows these strong cluster wakes downstream. We can also see the effect of the gravity waves, the oscillations. And then in comparison, our MSE model, the low-cost, very, very low-cost engineering tool, it doesn't have that. The wakes in the MSE model recover much, much more quickly, and they don't live nearly as far downstream as what we see in our LES. And so this is another deficiency that we need to rectify. And so to address this, we wanted to add in a shear stress parameterization, or a better way to capture the long downrange wind recovery of the wind farm wake. So this is in the existing wind farm with an existing wake model, one that is currently used in engineering practice. And we can see that it has a little bit better predictive ability to capture the recovery, the long range recovery of the wind farm, but it doesn't capture the gravity waves nearly as well. And it doesn't capture the slowdown upstream of the wind farm as well either. And so we want to add in some features of this wake model to our multi-scale coupled model to make something that's kind of a super model that can be used for very high fidelity predictions. And in doing this requires for us to model the shear stress along it, like near the surface of the ground, near to and the mixing of the shear stress downstream of the wind farm explicitly. And so this is the development of the next step. So what we've shown here is a slice through that LES, and that shaded region we average horizontally, and we've plotted the shear stress as well as the wind velocity. But what we see is that there's a much more gradual recovery of the stress than there is of the velocity. And we need to better capture the stress, the shear stress in the wind, which is relating to the delay in the wake recovery. So to capture this, we wanted to capture the interlink between the velocity and the shear stress, and that requires additional work. So as far as the velocity in the wind farm, there are existing models that can be used, and there's some newer ones by Stark and a few other collaborators that are called top-down models that do a good representation of the flow within the wind farm. And we wanted to adapt these. They're made for velocity, and adapt them to be used for predicting the behavior of the shear stress within the farm. So the way that the existing top-down models work is they assume that the velocity profile within the wind farm follows different behavior in different layers. So in the layer that's nearest to the wall, they assume that the velocity behavior there follows what's called a law of the wall turbulent boundary layer. Within the region covered by the rotors of the wind farms, they have a certain logarithmic profile. And then in the region above the rotors, they have another logarithmic profile that corresponds to the velocity, the development of an internal boundary layer that begins at the first rotor and continues downstream and then ends at the last rotor, and then there's another recovery. And so this recovery length scale depends on the internal stability of the boundary layer. And then we have different parameters that we can use to tune the shape of these velocity profiles within that farm. And this allows for us to correct the velocity deep within the wind farm, and it's called the deep array effect, and it allows for us to capture non-uniform fields in speed and in direction, as shown by this image. And we wanted to adapt that to not just model the velocity, but then also to model the shear stress. And so we're adapting an idea from other researchers. They modeled the velocity in different layers. We wanted to have the same concept, but applied to the shear stress. So we have a background stress layer far above the wind farm. We have a high stress layer that is the region where there's high turbulent entrainment. We have a wind farm layer where we have interactions between the different wind farm wakes, and then a low stress layer very near to the wall. And then by imposing different constraints on these different layers, we generate a piecewise linear approach for modeling the shear stress in these different layers. And within the farm wake, there's a certain high and low value for these shear stress amounts, and there's an exponential decay that occurs downstream of the farm. We've tuned that using our large eddy simulation model with an aligned wind farm. I'm not going to go into great detail here because we already talked about how we use this large eddy simulation model for generating large eddy simulation results of the wind farm interacting with the atmospheric boundary layer. And here's the results. So what we have in the black, as well as the the individual symbols are our large eddy simulation results. And then the blue and the orange corresponds to our shear stress model, the parameterization. And it's a piecewise linear model. And despite being relatively simple, just piecewise linear in these different layers, we can capture the stress within the farm reasonably well. And so row 1 to 20 corresponds to the stress that's observed on average in time at those different turbine locations. And we can capture the stress reasonably well. And then 5D to 55D corresponds to that many rotor diameters downstream of the last row of turbines. And we can capture the recovery of the stress downstream of the wind farm much, much more accurately, using even despite it just, it's a simple piecewise linear stress parameterization. The right-hand side image corresponds to the velocity profile, where we can see that also the parameterization does a good job of matching our large eddy simulation result. So now that we've applied this, we can, or now that we've developed this, we can apply it to any arbitrary shape of wind farm. And we need to know how to capture the thrust of the individual wind turbines. And to do that, we need to know how far spaced the wind turbines are. And that's not necessarily automatic when you have a very arbitrary configuration like a real-world wind farm cluster. So we developed a spacing algorithm to detect the distances between individual wind farms within a farm. And we treat each wind farm as an individual isolated wind farm, and then we superimpose the sum of the deficits of the adjacent farms. And we found that that works very well. The individual farm clusters interact in a relatively linear way, whereas the farms interacting with the atmospheric boundary layer is quite nonlinear. But if we can capture the nonlinear interactions for each individual farm, then the mutual interactions between the farms in their wakes downstream can be captured in a relatively simple way. Let's go on to the next slide. So this presents just a brief view of looking at our results. So if we have a top-down model, that's the model without a proper capture of the stress that we've applied, the gravity wave effects are not present when you have a homogeneous background wind. If we apply the top-down model and we allow the background wind to capture the gravity waves, then we see the gravity wave effects. We get the upstream blockage upstream of the farm, that's the reduction in power, but we don't capture very well the far wake effects, and the large-scale wakes are not properly resolved. So integrating the multi-scale coupled model with a shear stress parameterization can resolve. So this is, again, another description of how we resolve our gravity wave effects. And we do it by vertically displacing the top boundary based off of the displacement of our inversion layer from the atmospheric boundary layer that was predicted according to our multi-scale coupled model. We've run two cases for this arbitrary wind farm under a conventionally neutral boundary layer, as well under a stable boundary layer under different inversion temperature differences using our in-house code. So again, here are the results, and these results come from our large eddy simulation, and we're comparing them to our top-down model. And the model demonstrates that the velocity deficit is not well predicted within the wind farm. The wind farm vertical profile is captured reasonably well. The velocity doesn't recover very well, and so we wanted to improve these with a better sense of the shear stress effects. So this, again, is presenting our shear stress. We see that the large eddy simulation data agrees reasonably well with our shear stress parameterization within the farm. And then downstream of the farm, we get reasonably good recovery. The shear stress is slightly overestimated within the farm, but the evolution within the downstream wake is very nicely captured, and the shear stress recovers within 50 kilometers downstream. And so we would expect the wind farm not to interact with its neighbors very much beyond about that 50-kilometer distance under these conditions. All right, so then when we couple our wake model for the wind farm with our multi-scale coupled model, the solution inside is dominated by the wake model. The solution in the wake is dominated by the shear stress parameterization, and the global blockage is well captured in our original multi-scale coupled framework. We can also look at the wakes being deflected, although the wake deflection is slightly underestimated presently. So essentially what we're showing here in this slide is the culmination of all the different parts that we've put together. We've looked at the interaction with the atmospheric boundary layer and how wind farms trigger gravity waves within the atmospheric boundary layer, and we can see those in our large eddy simulation. We see how wind farms generate a wake, and that wake mixes out, and how adjacent farms can have interacting wakes, and we see that in our large eddy simulation as well. And then we're also able to create very low-cost predictive tools to model the effects in an engineering sense. So to provide context, the top image here is a large eddy simulation that was run on 80,000 plus CPU cores for 40 hours. The bottom one was run on one CPU for about 30 seconds, and we get in MATLAB, and we get very, very good agreement. And so by understanding the complex physics of this problem, we were able to make mathematically kind of cheap predictive tools to understand, and that this would give us better fidelity in predicting and understanding the behavior of wind farms when we're doing site assessments and other types of activities. So to conclude, wind farms and the interactions between wind farms and the atmospheric boundary layer is very complex and very interesting. The global blockage that we see created by the wind farm is driven predominantly by the creation of atmospheric gravity waves in the boundary layer, and that is strongly dependent on the potential temperature profile. So how much variation in temperature there is within our atmospheric boundary layer. Gravity waves are complicated to capture in a numerical simulation, but if you handle them carefully, they can be resolved. We showed that you can model the effects of gravity waves in a very cheap way when you account for the perturbation of the inversion layer in your numerical simulation. We were able to demonstrate that a coupling between individual models at the turbine scale for wake effects and blockage effects with the behavior of the atmosphere at large scales and coupling them in an interactive way allows for us to predict the power in a wind farm and the losses created by gravity wave interactions with the atmospheric boundary layer. And we were also able to demonstrate the creation of a very cheap wind farm wake model to address the interactions between adjacent wind farm clusters and capture that in a very cheap way. So the take-home message I hope everyone can receive from this is wind farms are very interesting, and the way that they interact with the atmospheric boundary layer is highly interactive, highly complex, and requires very sophisticated large-scale numerical simulations to understand properly. But when we develop the right tools to make those understandings clear, then we can use that insight to make low-cost mathematical models that can be used in an engineering context to do more accurate site assessments, as well as to look at the control of wind farms. And moving into the future, that is the kind of research that my team would like to get into. Now that we can predict the behavior of a wind farm almost in real time, how would that inform the way that the wind farm operator operates the wind turbines? Is it possible to get an overall improvement in the operation of multiple wind farms by, for example, reducing the power output of an upstream farm to better optimize the power from a downstream farm? And interacting or operating wind farms in an interactive way over a large geographical region is an interesting concept, one that can be investigated using the tools that my team has developed. So I want to thank everyone for your attention, and I especially want to acknowledge the graduate students from my team who have worked very hard in creating a lot of these tools. Mohammed, Sebastiano, Arjen, they're all PhD students or former PhD students. I need to acknowledge the Research Alliance of Canada, as well as UBC. Thank you again.
Perfect. Thank you so much, Dr. Brinkerhoff. That was an amazing lecture, and thank you again for being patient with some of our issues we had with our slides. But I think we have a little bit of time left, so I'd like to open it up to questions from the audience. So just a reminder to our audience to use the question icon to the right of your screen to ask any questions. And yeah, we'll get a few in right now before we have to go. So our first question comes in from one of our audience members, Scott. Scott asks, would your model be able to identify wake differences between turbine designs? For example, the difference between the standard 3-blade tower and one that may be a vertical oriented one, or maybe have more than 3 blades.
Yes, so I'll answer that question in 2 ways. The first one is yes. The difference that these in the wakes of these different turbines we could easily capture if we were to simulate the individual geometry of each of these different types of turbines, which we can do. Our Tosca code allows for us to input the actual shape of the blades, whether it's a horizontal axis turbine or a vertical axis turbine or any other kind of turbine that we want, and capture the wake created by that novel turbine shape. So in that sense, yes, we can capture those wake differences. However, when we're looking at wind farms, currently the cost of the simulation is so high that we can't resolve individual turbines in that way. So we have to account for the effect of individual turbines. And we do that using what's called an actuator disk. So we replace the turbine with a disk in space that removes momentum in a manner commensurate with the power removed by that turbine. So in that case, we need an actuator disk model that's tailored to whatever novel turbine design that we have. And then the same thing goes for wake models. And so we would be able to generate those wake models and actuator models by doing a resolved simulation of the novel turbine design, and then input it into our code and then use it for predictive tools. But it wouldn't be direct. It's not automatic. So to answer the question, Scott, the answer is yes, and no, and yes, but it would take a little bit of time.
Perfect, thank you. Our next question comes in from Sam in the audience, who says, do you take into account surrounding terrain variations?
Wonderful question. What was the name of the asker, Claire?
Sam Rondeal.
Sam, wonderful question, Sam. Terrain is really critical, and I'm glad that you pointed that out because uh, onshore terrain will also trigger gravity waves. So if you have, like in southern Alberta, wind farms that are, let's say within 50 or 100 kilometers of mountains, you're going to have gravity waves being triggered by those mountains, interacting potentially with the gravity waves triggered by the farm. And the question, of course, is which type of gravity waves are going to dominate, and how do we capture that, and how do we model that interaction? And that lends itself into a much more complicated area where we're going to have to broaden the domain of what we're simulating to account for nearby terrain, as well as the terrain that the farm is sitting on. The terrain of the farm will also have an effect. So I didn't present any of the work in those questions, but that's the next phase of our research as well, where we're running simulations in real world terrain and looking at gravity waves triggered by the terrain, looking at the interaction of the terrain with the wind farm and the interactions with the atmospheric boundary layer. And then the goal is to be able to have these low cost engineering tools also account for all the terrain effects, the terrain interacting with the boundary layer, the terrain acting with the farm, and then that kind of mutual interaction between all three.
Perfect, thank you. We actually have two questions from our next audience member, Russell. So the first question Russell asks is, do you predict this having significant impacts to wind farm design philosophy, or will it see more impact in operating philosophy?
I think it's going to have a bigger impact on even before the wind farm is made. Site assessment is really, I think, where these tools are going to be the most impactful. Better, more accurate assessments of what the wind energy potential at a given site is. And that's good news for everybody, because when a wind farm developer wants to build a wind farm in a site, knowing very accurately how much energy they can produce is really important. And I think the bank that lends them money to build the farm cares about that as well. I think the other place that it would be have an impact is on the operational side, as was mentioned, less so on the design. I think the design is constrained by many factors, including the ability to have electrical interconnect and the site constraints and so forth. Offshore, there's also installation challenges, etc. But once a site is there, we could optimize its operation with the insights provided by the more higher fidelity predictive tools that my team produces.
Okay, fantastic. And then Russell's second question is, will your engineering model be available for developers/engineers in the industry to use to model wind farms, or is it intended to be incorporated into existing software like OpenWind?
Both. We are releasing the model as an open source in the literature. At the same time, the model is being integrated into OpenWind, and we're involved in that. That's our industry partner. And so it's going to be available for everyone if you want to incorporate it into an in-house tool, but it's also going to be on offer within OpenWind's commercial offering as far as a site assessment software is concerned. My hope is that the literature or the research will show that it's a useful tool, and then it will be incorporated into WASP and other site assessment software soon.
Perfect, fantastic. We have two more questions, so conscious of time, I'm hoping we can get these two in. So the second last one is from Andy, who asks, can the simulations design a most efficient wind turbine array?
It would be hard to say it can be most efficient. We haven't introduced any kind of optimization algorithms, but what we can definitely do is run different types of turbine arrays and assess them in terms of the overall performance. To get the most efficient one, we would need to introduce an additional optimization layer, I think, which would be interesting.
Perfect. And then another question from Jason. What is your view and potential timeline for the use of this model in industry for development, siting, and energy modeling, particularly whether you are working with industry partners to get this implemented in modeling software packages?
Yes, and the answer is the timeline is very quick. It's already implemented in OpenWind in a kind of beta version. OpenWind is a software that UL Renewables sells, and there are industry partners, so they've supported this work, and they're using it presently in its kind of beta stage for some existing customers just to test its viability in kind of real world conditions. So it will be available, in my estimation, for the industry to use early in the new year.
Perfect, thank you. And we actually got one more question that came in at the last minute, so I might ask this one as well. So this comes in from Colin. So Colin says, you mentioned an interest to get industry involvement in control methodologies to optimize production between farms using these models. Is the MSC model as useful for simply optimizing operation of individual turbines in a single farm? You may start with that. There is a bit more. But...
Yeah, I didn't catch the last part of the question, Claire. Could you read that last part again?
Yeah. Is the MSC model as useful for simply optimizing operation of individual turbines in a single farm? He then goes on to say it may be a difficult ask to optimize collections of farms, given that in many cases the operators of different farms are different companies with little incentive to cooperate.
Yeah, I appreciate that. That's very true. It could be used for that, but it could be used for wind farm control. But that would require operators to work in some kind of collaborative fashion. And so whether it would be used for that or not, I think is somewhat dependent on like kind of the industry environment. But it has the capacity to be used in that manner.
Great. There is a second part, so I'll ask that as well. Secondarily, will perhaps the optimal design of a single farm change with a cheaper model? Example, maybe the turbines will not be laid out in a perfect grid.
Those are very good questions. I think the optimum layout incorporates a lot more constraints than what my model looks at, which is focused on the aerodynamic interactions with the atmospheric boundary layer and the surrounding turbines. We didn't take into account any of the how constrained in space is there. What are the geographical interactions? Siting roads and connecting to the electrical grid, etc. So I think that if we did want to kind of optimize wind farm layouts, incorporating other constraints, not just the aerodynamic ones, we would have to add in additional factors. And then other things that my model is not at all currently investigating at all is like aeroelastic effects and noise. And there's a lot of things that haven't been investigated yet. Others are looking at those kinds of questions. My questions that I'm most interested in are kind of the larger scale nonlinear interactions between large wind farms and the atmosphere, and understanding that understanding that complex process.
Well, thank you so much. That is our last question that we have from the audience, and I see we're a little bit over time, so I just wanted to take a moment to thank you again so much, Dr. Brinkerhoff, for joining the SpaceLab Speaker Series today, and for your remarks and answers. This is such an interesting talk and such a relevant topic for us here at ATCO. So I also want to thank all of the ATCO colleagues who are involved in putting this event together, as well as everyone in the audience who's joined us today. We very much appreciate your interest and invite you to watch our social media feeds for information about future ATCO SpaceLab Speaker Series sessions. I'd also like to remind you that all lectures that this lecture along with all past lectures that we have are shared on our ATCO YouTube channel. And with that, I'd like to just encourage everyone to stay safe and enjoy the rest of your day. Thank you so much.
Thank you.